For problem number 25, you can read the problem, but the main thing is all the stuff is on the picture already. We want to know, find the height of the mountain here, which is x. So the vertical and the horizontal are always going to make a 90-degree angle, but I don't have enough measurements on this picture. If I could find this length, I'll call it y, or this length, I'll call it z, I would be able to do some sine, cosine, or tangent. So my first thought is, how can I find side y? Because I can find lots of the angles, actually all the angles in this picture. If this angle right here is 27.5, that 27.5 makes a linear pair with the angle right next to it, so this angle is going to be 152.5. And if I have 152.5 plus the 11.5, that's a total of 164. Subtracted out of 180 is going to leave me 16 degrees for this angle up here at the top. Now the reason that's important to me is because it tells me I was driving at ground level for 5 miles. So this length from where I took the 11.5 over to where I stopped and took the 27.5 degree measurement is 5 miles. And that 16 degrees is opposite the 5. So I could say 16 opposite the sine, 16 was the angle, excuse me, we don't want to do it that way. We would say 5, the segment, over the sine of that 16-degree angle should equal that side y that I'm looking for, which is across from the 11.5 degrees, so the sine of 11.5. So I'm going to use a law of sines to find that side y from where I stopped to the top of the mountain. And I'm going to solve this. So I cross multiply, I get y times the sine of 16 is equal to 5 times the sine of 11.5. So to solve for y, I have to divide by the sine of 16. So into my calculator, I'm going to type 5 times the sine of 11.5 equals, and then divided by the sine of 16, and I'm getting that y is equal to 3.6. Well, if y is 3.6, I'm going to add another page here so I can see this better. If y is 3.6 and I'm looking for the height with a 27.5 degree angle over here, this is your basic sine, cosine, or tangent. I could use law of sines again if I wanted to, but this should be good enough to use an opposite over hypotenuse, which would be the sine of that 27.5 degrees equaling the height x over the 3.6 that I just figured out from y. So the sine of 27.5 is 0.4617 equals x over 3.6. So I think of it as over 1. I multiply, I get x is equal to 0.4617 times the 3.6, which gives me 1.7 when I round to the nearest tenth. So the height of that is going to be 1.7. So you're thinking 1.7, that doesn't make any sense. How can a mountain be 1.7? Well, we're talking in terms of 5 miles. So when you figure this out, you're saying this is 1.7 miles high. And 1.7 miles straight into the air is a fairly tall mountain. So that does make sense, and it is the correct answer here. Problem number 26. We explained this in class. I want you to be able to explain it at least a little bit in your own words. Explain why the law of sines works. So on this one, what I want you to understand is that everything revolves around h, the height of the triangle. For example, the sine of A is equal to h over c. But the sine of c is equal to h over a, the opposite over the hypotenuse. So I've worked into the equation sine of a, sine of c, c, and a. But I want to get h out of there. So what we do is we multiply both sides of both equations by h. And what this does for me, I'm sorry, not by h. Let me back up a step. We multiply the denominator. So in this top one, I'm going to multiply by c. We're going to solve for h. So I get this equation that says h is equal to c times the sine of a. And I'm going to multiply by a in the second equation. So I'm going to end up getting this idea that h equals a times the sine of c. And then we use the transitive property. If both of these things equal h, then they should equal each other. So c times the sine of a should equal a times the sine of c. So that part's good. We've got all the pieces, but it doesn't look like the law of sines. So the last step is we divide both sides by the sine of a and the sine of c. So sine of a and the sine of c. And what happens is the sine of a cancels the sine of a, just leaving me c over the sine of c. And on the other side, the sine of c cancels the sine of c, leaving me just a over the sine of a. And I've proven that every time in this triangle, this relationship will hold true. And that's the law of sines. All right, and then the last two problems here, you have to use the law of cosines. In fact, the last three problems here, you have to use the law of cosines, and it will be that way on the test. Law of cosines only works when you have a side, angle, side relationship, or like in 22, where you have a side, side, side. So let's start with the easier one, side, angle, side, number 27. You need to know the formula says that the opposite side and its angle should start and finish the law of cosines. So it'd be a squared equals, and then we should end with the cosine of 58. So I start with a and end with its opposite angle. Everything else in between is the other two numbers, 4.7 and 12.3. So it's going to be a squared equals 4.7 squared plus the 12.3 squared minus 2 times the 4.7 times the 12.3 times the cosine of 58. So you need to understand all of this is one number. So I'm going to type this into my calculator. 4.7 squared would be 22.09 plus 12.3 squared is 151.29 minus, now I'm going to type all of this into my calculator, 2 times 4.7 times 12.3 times the cosine of 58 gives me 61.27. So I'm subtracting that from the other two. So this is equal to a squared. Well, I just need to put this in my calculator. 22.09 plus 151.29 minus 61.27 gives me 112.11 equal to a squared. Well, I still have to square root to figure out what a is. So the square root of that ends up giving me 10.58, which we're going to say is close enough to 10.6. Now, if I want to find an angle, I would just use the law of sines now. Because if I know angle A is, if side A is 10.6, I'm going to use a law of sines that says 10.6 over the sine of its opposite angle should equal angle B, so 12.3 over the sine of angle B. I cross multiply, I get 12.3 times the sine of 58 should equal 10.6 times the sine of B. So I have to divide off the 10.6. So when I do that, I take 12.3 multiplied by the sine of 58 equals, and then divided by the 10.6, I'm getting that to be about 0.9840, and that should equal the sine of B. So here's where I have to do the sine inverse of that number to figure out what the actual angle B is. So I take the sine inverse of that 0.9840, and I get that angle B must be about a 79.7 or 80 degree angle. And that's how you do it if you have a side angle side relationship. In problem number 28, you have a side 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 relationship. So let me put this on the bigger page because it gives me a little bit more room to work. So we've got sides of 2, 14, and 9. Well, 2 and 9 only add up to 11, which is not bigger than 14, so this is impossible. But that doesn't help you, so let me give you an example that is possible. So let's just turn this 2 into a 12. And now we'll do it that way. So if that was sides of 12, 14, and 9. So we have a triangle, sides 14, 12, and 9. And we want to know what are the angles A, B, and C. I'm going to put this into a law of cosines formula. Let's find angle A first. If angle A is what I'm looking for, that's going to end my law of cosines. So the cosine of A will end the formula, and 9 is across from that, so 9 squared will start it. Because the law of cosine says 9 squared should equal 12 squared plus 14 squared minus 2 times the 12 times the 14 times the cosine of A. And again, I need to point out, this is one giant number. So you can't add that stuff together. What I can do is say 9 squared is 81, 12 squared is 144, 14 squared is 196. I can go ahead and multiply the 2 times the 12 times the 14, so it would be minus 336 times the cosine of A. But again, that is one number. So I can't add that with the 196. The 144 plus the 196 I can add together to get 340 minus 336 times the cosine of A equals 81. But I cannot subtract the 340 and the 336 because this has a variable, this has a multiplication. So I can't do that. What I need to do is subtract the 340 to the other side to get this variable of cosine of A by itself. So 81 minus 340 is negative 259, and that should equal negative 336 times the cosine of A. Now I can divide off the negative 336 to get the cosine of A completely by itself. So negative 259 divided by negative 336 gives me 0.7708 equaling the cosine of A. So I need to do the cosine inverse of that decimal to figure out what angle A is. So the cosine inverse of that gives me angle A to be about 39.5, which we're going to call then 40.0 degrees. And all of that is just to figure out angle A. So angle A is 40 degrees. Now that I know one angle, though, I should be able to use law of sines and make this much simpler for myself the rest of the way out. Because now I know that 9 is opposite the 40, so 9 over the sine of 40 should equal 12 is opposite angle B, so say 12 over the sine of angle B. Much easier to do this now than law of cosines again. So 12 times the sine of 40 should equal 9 times the sine of B. I have to divide by 9. So when I do that, 12 times the sine of 40 equals 7.7 divided by 9 is 0.8570 equals the sine of B. So here again I have to do the sine inverse of that decimal to figure out what B is. So when I take the sine inverse of that 0.8570, I end up getting angle B is 58.98, which rounds to 59 degrees. So that would be a 59 degree angle. Well, now the third angle is simple. If I've got 40 degrees and 59 degrees, that's a total of 99 degrees. Taken away from 180 only leaves me 81 degrees for the third angle. And that's how we use law of cosines to find that missing angle, or all three missing angles when I have a side-side-side relationship. And the very last problem, number 29, is also a law of cosines. So I'll sketch it out and then I'll make it bigger so I can see the work. It says two airplanes leave an airport. So let's call it A for airport. And the angle between their flight paths is 40 degrees. So this plane goes this way, this plane goes this way, and between them is a 40-degree angle. An hour later, one plane has gone 300 miles and the other has gone 200. How far apart are they? So how far apart are they? So this is a side angle side relationship, so it's going to require law of cosines one more time. So let's look at law of cosines one more time. We've got 300 miles away, we've got 200 miles away, and they were going at an angle of 40 degrees. So how far apart are they? Again, law of cosines works by saying the side squared should start the formula and the angle that it's across from should end the formula. So the cosine of 40 should end it. Everything else in the middle uses the 200 and the 300. So it's going to be 200 squared plus 300 squared minus 2 times 300 times 200 times the cosine of 40. So this is one where I get to just type it all in. 200 squared is 40,000 plus 300 squared is 90,000 minus 2 times 300 times 200 times the cosine of 40 is 91,925.33317. And again, reminder, this is one number when I type it into my calculator. So this should all equal x squared. So I'm just going to keep going. I'm going to add all this together now. So 40,000 plus 90,000 minus the 91,925.33317 gives me 38,074.66683. So the last thing I have to do is square root to figure out what x is. So when I square root that number, I get 195.1 miles apart. So that's how we use the law of cosines when it's a side-angle side relationship.